Yeah, everyone. Next part of chapter 14, we're going to talk about triple integrals. So up until now, we've only dealt exclusively with double integrals, which is a good little introduction to how diff integrating works in functions of several variables. In addition to that, we're also going to look at different applications that involve both double and triple integrals. Um, One kind of thing I want you to have as a goal for this is to look for patterns, right? When we're looking at these application problems, the thing is, you see the same kind of patterns happen over and over again, and it can even transcend fields of study. Like, one of the things we're going to look at is going to be heavily physics-based, but there are parallels to even statistics and anything that actually uses graphs of functions to get information. So with that said, we're going to start off with a simple one. What are triple integrals? How do we set them up? And how do we find volume? So triple integrals work pretty much the same way that double integrals do in that we start from the middle and we work our way out. We also have to be very weary, very careful of the bounds on an integral. Remember, with double integrals, if you had a variable in your bounds, then the other variable had to be the differential. By the time you get to the end of it, none of the variables that were in the differentials should be in your answer. Same thing applies with triple integrals. The only thing is now that we have three, our innermost integral can have bounds that involve the other two variables, right? So if dz were my first differential, then my bounds could be for the first integral, or the innermost integral could be in terms of x and y. Right. And then as we go on, like if the next differential were dy, then x would be the only permissible variable in the middle integral, right? And then by the time we get out to the end, there should not be an x, a y, or a z in any of the bounds. All right. So the way that we kind of defined integrals of two functions, right, double integrals, was that they were the limit of the sum of volumes, well, yeah, volumes of boxes, right? And we had our differential dA, which corresponded to changes in the area of the base of the boxes. Now that we're looking at triple integrals, we can define volume as the triple integral over our base solid, right? So it's not like double integrals, we had a base area and then we kind of extended in the z direction, right? With these, since we don't really have a way to visualize four-dimensional objects, it's kind of hard to explain in that same way. But think of it as now the basis is a three-dimensional object and it's expanding in some fourth dimension that we can't really visualize. Um, but anyway, we can calculate volumes. So remember earlier in this chapter, we looked at using double integrals to calculate volumes. Well, if you look back at some of those examples, you could actually rewrite a lot of them as triple integrals. You could rewrite all of them as triple integrals. So let's look at an example. Find the volume of the ellipsoid given by that function. So I know that since we're in terms of x, y, and z, and we're not changing into polar or, well, not really polar, that doesn't work for triple integrals, right? Um, since we're not changing into a different coordinate system yet, we would just let our dv be dx, dy, dz in whichever order we want to do it. I would recommend having dz as the innermost. And the reason for that is that I can actually solve for z slightly more easily than I can solve for x and y. So, um, with that said, if I move these two terms to the other side, I get this. Notice that you can actually factor a 4 out. That's going to be important because when I take the square root of both sides, I get the absolute value of z equal to the square root of all that. If I factor my 4 out, then we get the following. And because I have a perfect square times this, I can take the square root of 4 out. So 2 times the square root of 4 minus x squared minus y squared. Close that off so I'm not a heathen. All right. So this is why I would have z be my innermost differential, because this gives me an expression in terms of x and y, meaning it has to be the inner bound. So we're going to integrate from 0 to 2 times the square root of this guy. All right. And then, let's see, from there, all right, from there, we kind of have a bit of a choice on what we can do with, yeah, we have a bit of a choice of what we can do with these other differentials. All right, so with that said, if I were to look just at what's left when I take out this z part, right, I can divide every term by 4. Right, and then I have a choice. I can solve for either the x or the y, yep, in terms of the other one. And the route that I choose is going to dictate whether I do dy dx or dx dy. So in this case, for fun, let's solve for y. So I would end up getting y squared is equal to 4 minus x squared. And if you think about that, this essentially corresponds to a circle. Then square rooting both sides would tell me that the absolute value of y is equal to the square root of 4 minus x squared. Right? I'm writing absolute value as opposed to writing a plus or minus in front of the square root. So with that said, I know that my y's are going to range from 0 to this guy, square root of 4 minus x squared. Okay. And then the last part of this is to figure out what the range of values are for x. So if we were to analyze this shape a little bit, we know from way back in chapter 11 that to write this in a standard form, we would have to divide every term in the equation by 16, because we need this to be equal to 1 to be able to pull things like the radius in each direction. All right. So then, yep. So then when I do that, if I divide every term in the equation by 16, I get x squared over 4 plus y squared over 4 plus z squared over 16 equals 1. So that means that the radius in my x direction, which is what we're going to need to set these bounds up, is 2, the square root of 4. All right, now with that said, we know that yeah. With that said, we know that the values of x are going to range from 0 to 2. Now, other thing I want you to notice that I haven't really mentioned at this point is that I've only considered positive values for each, don't forget that one, for each of the, um, what's it called? Coordinates, right? So I'm only considering positive values for x, y, and z. The reason I'm doing that is mainly to ease the amount of computation I have to deal with, because if I have negatives here, then what's going to happen is when I go through and take these antiderivatives, we're going to end up getting some pretty gnarly things involving square roots that we just don't want to deal with at this point in our lives. So other than that, I know that I'm able to take this kind of shortcut because of the symmetry of this ellipsoid. I want you to notice that the x, the y, the z, none of them have anything being added or subtracted, which means that this is an ellipsoid that is centered at the origin 0, 0, 0. And if I were to draw that out, we would basically get like this really tall, I mean, it kind of looks like plankton if you're a SpongeBob person. All right, can draw the antennas and the one eyeball and the evil grin. I'm having too much fun with this. Anyway, the point is that you can see that this is going to be symmetric, right? Whatever the volume is in this first octant is going to be the same as the volume that's in all of the other octants. And as the name suggests, there are 8 of them, right? You have this corner, you have this piece behind the wall, you have this piece behind the wall and behind the corner, you have this piece on the other side, and then you have those same 4 below the floor, right? So, I wonder if you'll ever get that recipe. Anyway, if I want to find the volume of the entire ellipsoid, I would need to take the triple integral that I set up here and multiply it by the number of octants. And that's just in this case, we can use symmetry to make our lives easier kind of thing. Right? Everything that we've said kind of setting up this integral, it still applies, right? If you were to write this out and you didn't just say absolute value, you wrote plus or minus, you could have -2 square root of stuff as the lower limit, and negative square root of 4 minus x squared, and -2. And you would end up with the same answer, but the amount of things that you'll have to type into your calculator will be a lot higher than someone who takes the shortcut because they recognized the symmetry of plankton. Okay, so at this point, we're just evaluating the triple integral. So we start with our innermost integral, right? So antiderivative of 1 dz is just z, okay? And then we're going to plug in top minus bottom to z. That's going to end up giving us just the top because we'd be subtracting 0. So we have 8 integral from 0 to 2, integral from 0 to the square root of 4 minus x squared. And now the result was just 2 times the square root of 4 minus x squared minus y squared. And we still have dy dx to deal with. All right, so for the next part of this, yep. So for the next part of this, there are a couple of options we have. We could technically evaluate this piece by converting to polar coordinates, which we've talked about already. Right, but keep in mind that would only address the, what's it called? Innermost integral, right? You would still have to integrate from 0 to 2 with respect to x, which would mean that if you converted to polar and then you got your answer, you would have to convert back into rectangular, which I mean isn't terrible, right? But in the textbook, they basically just say, here's an integral table. We know the antiderivative of this. So I'm going to show you all that. So I know that, so based on what the textbook tells you, we have 8 integral from 0 to 2. We still haven't done the outermost integration yet. The antiderivative of this with respect to y is y times this square root exactly as is plus 4 minus x squared times sine inverse of y over the square root of 4 minus x squared. And we're evaluating that from y equals 0 to y equals the square root of 4 minus x squared. Okay, we're going to do some boxing off here at minimum. I'll probably find sheet of paper. I'll use the back of that one. So continuing, okay, here we are. All right, so continuing, I'm basically going to plug this in anywhere that I see a y, plug 0 in anywhere I see a y, and then subtract the results. So we have 8 times the integral from 0 to 2. Here's the convenient thing, though. If I plug in the top number, right, the inside of the square root becomes 4 minus x squared. I'll write that out. 4 minus x squared minus 4 minus x squared, right? Because if you square this, the square root goes away. So that means that this whole term, which I should have also written 4 minus x squared here, which is why I didn't want to write that term. This whole term is going to be 0. Pretty fun. For the next term, we have 4 minus x squared multiplied by inverse sine of the square root of 4 minus x squared divided by the square root of 4 minus x squared. Now, what is the square root of 4 minus x squared divided by itself? It's 1. And we can do sine inverse of 1, right? What angle has a sine value of 1? Hopefully we all emphatically said pi over 2. So that whole inverse sine factor is just pi over 2. Pretty cool. Okay, and then from that, we're going to subtract what we get from plugging in 0 for y. So in this case, y times the square root of blah, blah, blah is going to end up being 0 because y is 0. Aren't you glad we used the symmetry of Plankton? I know I am. Similarly, if I plug 0 in for this y, we end up taking inverse sine of 0. Now, what angle has a sine value of 0? Hopefully we all emphatically said 0, because that's true, which means that this term will also be zeroed out. So when I plug 0 in for y, I still get 0. That's pretty fun. And at this point, if I make this a little neater, we have 8 times the integral from 0 to 2 of basically pi over 2 multiplied by 4 minus x squared. Everything else in that integral was 0. So if I take that constant out, I get 4 pi, and I can take the antiderivative of this just using my power rule. So we have 4x minus x cubed over 3, and we're going to evaluate from x equals 0 to x equals 2. And luckily, if I plug 0 in, the whole thing is 0, right? So I really just need to plug 2 in. So I'll get 4 pi, my factor that's waiting outside. 4 times 2 is 8, minus 2 cubed over 3, so minus 8 thirds. And then if we math this a little bit, that's 24 thirds. If I subtract 8 thirds from that, I get 16 thirds. So we have 4 pi times 16 thirds. And if I multiply 16 by 4 pi, I get my answer, 64 pi over 3. And just like that, we found the volume of plankton.